Hello everyone and welcome to another video in my channel, and in this video we will be continuing with our Raytracer, our basic Raytracer. So in our last video we rendered three simple spheres using our basic ray tracing algorithm, and those spheres were pretty basic, like no lighting and shading, just simple three flat spheres. In this video we will be adding lights to our scene, right? We'll be discussing about different lights. We'll observe how light impacts our viewing of the objects, how light interacts with the various kinds of surfaces, what different kinds of lights are there. We'll be considering three types of lights: ambient light, directional light, and point source light. And also we'll be considering different surfaces like matte object, shiny objects, reflective objects, and so on. So we'll start with matte objects and then we will proceed further. So yeah, without further delay, as always, let's get started. Okay, so we'll start with the types of lights that we'll be considering in our scene. So we'll start with point lights. So let's first understand what are point lights in a scene. So point sources of lights are nothing but light sources which radiate lights equally in all the directions. And an easy example would be a light bulb. So a light bulb would be a very simple example of a point source. So a light bulb will radiate or emit light in all the directions uniformly, and this light can hit anywhere in the scene and it can hit our object as well. So let's say this is our object, which is again our sphere, and let's say a light can come and hit here at this point. So that's pretty much a point light. So it can be a bulb, a street light, a piece of LED, anything like that in the scene which radiates or emits light in all the directions. So how do we mathematically define or describe the ray coming from this point source to our object? So let's say we have a source of light called Q and we have got 2 points P2. Okay, so now how do we define or how do we describe the rays of light which goes from Q to, let's say, P1 or P2? So the ray of light which goes from Q to P1, we will define it as a vector which goes from P1 to Q. The light rays that go from Q to P2, we will define it as a vector which originates at P2 and goes to Q. So mathematically we can write this vector as the vector which is originating at P1 and going to Q. We can write it as Q minus P1. So this will be Q minus P1 and this will be Q minus P2. So like this we can represent the light rays coming out of a point source of light, right? The other type of light source that we'll be considering in our scene is the directional light source, right? So a point source of light always have a fixed location or a fixed position. For example, this Q is a fixed location or a position for the point source of light. So this Q can very well be this light bulb which has a fixed position defined by the 3D coordinates. But this is not enough to approximate all kind of light sources. So what about the sun? So what about light sources which are far away from the objects on the surface of the earth? For the tiny points which are present, or for the tiny objects which are present on the surface of the earth, we cannot consider light to be a point source, but rather from the perspective of that tiny point on the surface of the earth, the light coming from sun always has a fixed direction. So this is what we call directional lights. So directional lights doesn't have a well-defined position in the world, but they are defined only by fixed direction. So they will always be defined by fixed directional vectors. That's it. We really don't care about their position in the scene. But here again, the definition of point source and directional light source is highly relative, and it also depends on the scale at which we are operating. So let's say we are modeling the solar system. So in case of solar systems where the objects are the planets and the stars like sun, at that point of time, in such a case, the sun pretty much becomes a point source of light, because just like the other planets, the sun also has a fixed position and it's emitting light in all the directions, right? So it all depends on the distance between the light source and the object, right? And the scale at which we are operating. So if we are considering the light from the sun from a point on the surface of the earth, sun becomes a directional light source. If we are operating at a large scale like the solar system itself, sun becomes a point source of light. So that's our directional light. So for directional light, doesn't matter what point we are considering, maybe it's P1, P2 or P3, doesn't matter. All of them will be pretty much, all of them, the direction of the light rays from a directional light source will be the same. Okay, so that's directional source of light. Okay, so now the third and the final light source that we will be considering in this video for our scene is ambient light source. So what is ambient light source? So ambient light source is the easiest of all the three to implement. So in order to understand ambient light, we will have to understand the nature of surfaces a bit. So all surfaces by nature reflect some part of the light and they absorb some part of the light energy falling on them, right? Each and every body around us in nature will emit some light. So they won't emit light by themselves, but they will kind of reflect the light that is falling on them from some other source, right? It's not their own light they are producing, but it's the reflection of some other light that's falling on them. It might not be a very strong reflection like a mirror or a reflective surface. It will be some sort of weak reflection that will happen. And we can extend it further. We can say that a light coming from a light source falls on some rough surface. It absorbs some part of the light. It reflects some part of the light in all the directions. So that light again falls on some other object, and again the same process happens, and it keeps on happening. Like that object, the second object absorbs some portion of the light and it reflects some portion of the light, and it continues happening, right? So this is the reason, if you like, if in a moderately lit scene or in a moderately lit surroundings, if you just look below your chair, you won't find pitch darkness, right? There will be some sort of light there. So this is the reason why that happens, right? Because of this ambient reflection or this weak reflection that is happening even from non-reflective surfaces like your wall, your door, a piece of plastic, maybe your laptop cover, and anything and everything, right? They will reflect some sort of light. So now if we want to model these things, or if we want to simulate this kind of light reflection, like light coming from one source falling on anything and everything, from there it's again reflecting in all directions, and maybe a ray of light falling on another object, and such reflection and partial absorption continuing. If you want to model this specific thing as it is, it will be a very tough thing to do, right? It will be extremely tough with lots of compute power. So how we will define ambient light is just by its intensity. What we will say is that ambient light is a light source which contributes some light to all the points in the scene. Just a constant intensity value. That's it. It's a gross oversimplification. We are highly oversimplifying ambient light, but that kind of works for a scene. So ambient light is nothing but just a constant intensity factor that we will add to the final resultant light coming from a point on our scene, right? So these are the three types of lights that we will be considering while rendering our objects in the scene: point source of light, directional source of light, and ambient source of light. So now what we will try to understand is the different types of surfaces that we'll be working with, right? So the first surface that we'll be considering is the matte surface. We'll be considering matte surfaces first because matte surfaces are the most commonly found surfaces in nature, right? So the most of the surfaces that you look around yourself is pretty much matte surface. So a matte surface is a surface which reflects light in all possible directions. So when a light ray falls on the matte surface, it kind of reflects it to all possible directions around it uniformly, and this phenomena is called diffuse reflection. So let's try to understand what happens when light falls on matte surface. A very good example of this would be shining a torchlight on a wall, because wall is one such matte surface. So what we'll be interested in knowing in this case is the amount of light energy that gets reflected back from the surface. So as I mentioned, all surfaces reflect back some portion of the light falling on them, and it absorbs some portion of the light falling on them. So in this case, we'll be particularly interested in knowing how much light energy, or what is the intensity, what is the fraction of the intensity of the falling light that it reflects back. So let's understand how it works. So one interesting thing we will try to understand here is that the fraction of the falling light's incident rays intensity that is reflected back depends on the angle that the falling ray makes with the normal at that surface, right? So let us consider a surface, right? Let's say this is the wall, and let's say a ray of light is falling on this surface. The intensity of the ray that gets reflected back depends on the light energy reflected per unit area of the surface, right? That determines how much intensity is reflected back. So greater is the light energy reflected per unit surface area, the more is the intensity of the light that's reflected back from the surface. So now what we'll do is we will zoom into this scene such that the area that we'll be considering is infinitesimally small, right? In that way, it will be very easy to understand what's going on. So if we look from at a macro scale, it's just a ray of light, right? We will zoom into the scene so much that even this ray of light becomes a cylinder, like it has a breadth. So let's do that. What we will be considering is something like this ray becomes something like this cylinder. So what I'm trying to say is that we have zoomed in so much that this ray now has got a breadth, right? And for simplification, let's consider this breadth is basically what intensity the light ray is falling on the surface with. So this is nothing but I, and this area of surface where it's hitting, let's say it's A. So now if you see that this width of the ray is almost equal to the area, right? So in this case, the energy of the light reflected per unit area is pretty much I by A, right? The light that will be reflected, or the energy of the light that will be reflected back from the surface, is pretty much proportional to the area. And in this case, I is almost equal to A. So if we just divide by this, like, it will almost be 1. So what's happening here is, since I by A is almost equal to 1, or it's actually I by A equal to 1 in this case, what's happening in this case here is the light energy per unit surface area that is reflected from the surface is equal to the light energy incident on the surface per unit area. Okay, so now let's consider the case where the light ray makes an angle to the normal, to the surface normal. So let's say now this is, let's say this is the surface normal, this is the incident ray that's falling on the surface, and we'll call it N, we'll call it L. Let's say we'll do the same thing again. We will again zoom in, we will zoom into the scene such that we are considering an infinitesimally small area, and once again this light ray has a breadth now. Now the interesting thing here is this edge of the light ray has to travel a longer distance than this edge of the light ray. As a result, what happens, this area that the light ray has to cover now, or the area that across which the light ray gets spread, increases, right? So for the sake of clarity, let's just call it A1, this A1, and once again the breadth of the light ray is still I, and this time the area increases, right? The area increases because the light ray now has to cover a longer area. What we can see is the more we increase this angle, the angle that L makes with N, the more the surface area the ray has to cover also increases. So now if we try to calculate the light energy reflected per unit area of the surface, that becomes I by A2. Now since A2 is greater than A1, I by A2 becomes less than I by A1, because in both cases the intensity of the light ray is same. So what we can see here, the more we increase the angle between L and N, the lesser is the amount of light energy reflected per unit surface of the area. In other words, if you shine a torch perpendicularly on a wall, that area of the wall will appear to be much brighter than if you shine the torch on that wall in a slanting manner, right? Because the light rays will have to cover a longer distance on the surface, or a longer surface on the wall, and hence the light energy being reflected from the wall per surface area would decrease, and hence it will appear less bright. So that's how the matte surface reflection works in short. And now what we'll try to find out here is the intensity I that gets reflected back in terms of N and L. So L is the light vector and N is the normal, surface normal, and also the intensity I of the, so IR, if I say I reflected, I need to find out I reflected in terms of N, the surface normal, L, the light vector. Again, the actual direction of the light vector will be this way, not this way, but okay, light vector, and the intensity of the incident light, right? So this is something which we need to do. So let's try to do that. Okay, let's once again draw a light rays and our surface. So I'll try to draw it a bit smaller this time because we'll be doing some calculations. So I want to just keep some space for that. Okay, so this is our surface, and this, let's say this is our surface normal, and this is our light ray. and it's making an angle. And so once again, let's consider the breadth of the light ray here, and another one is, let's say, here. And so this is the surface area it's covering, and this is pretty much the breadth of the light ray, and this entire thing is the intensity of the light. So this is n. Let's consider this p. This is the p where the light is falling. This is r. Let's just name this point r. Let's name this point q, and let's name this s. Okay, and yeah, we already know this is I. Okay, so let's say that the angle between the light L and the surface normal n is alpha, and let's consider this angle to be beta. Now let's try to understand a few things. What is this angle QRP? What is this angle? Let's try to find out. So again, what are we trying to find? What we are actually trying to find out is the amount of light energy that's being reflected per unit surface area, right? So this is what we are trying to find out. Amount of light energy reflected per area, per unit area. In other words, we are trying to find out I by A. This is what we are trying to find out, right? Because the greater this is, the greater is the intensity of the reflected light. So now the first thing that we would have to do is, let's try to find out this angle. Why I want to find out this angle will be clear very soon, but what we know is that QRP is a triangle, right? And not just normal triangle. So if you see this, so we have drawn this straight line RS in such a way that it cuts the ray at 90 degrees. So this is pretty much 90 degrees, right? So one of this angle in this triangle QRP is 90 degree, which is, so basically the angle PQR is 90 degrees. So that means, so our angle of interest, which is QRP, is nothing but 90 minus beta. And again, so alpha plus beta is also equal to 90 degrees, right? Why that is 90 degrees? Because alpha plus beta is pretty much the angle between the surface normal and the surface, which is obviously 90 degrees. So again, alpha plus beta is 90 degrees. So from here we can find out alpha, which is also 90 degree minus beta. So what we can say is that angle QRP is nothing but alpha, because alpha is nothing but 90 minus beta. Let's consider triangle QRP, like this triangle, separately, right? So what I'm going to do is, I'm going to slightly translate this triangle and make it look something like this. Okay, and we know that this angle is alpha, and so I just slightly translated and flipped this triangle, and now we will say that now what we know is that this is alpha, right? This is alpha, and this is 90 degree, and this is beta. This is beta. So this becomes P, this becomes P, this becomes R, and this becomes Q. If this is Q, then remember from here, like this is pretty much the breadth of the light ray, and this L went from the center of this line, right? So RQ is nothing but, or QR is nothing but I by 2. So this is nothing but I by 2, right? Once again, so this light ray perfectly bisects this line RS, the line segment RS, because This is the light ray whose breadth we are considering. So RQ is nothing but half of RS, and RS is I. So RQ is I by 2, right? And now, what is RP, the hypotenuse? The RP is nothing but half of area, A by 2. So if we take the ratio of base by hypotenuse, that is I by 2 divided by A by 2, 2 and 2 cancels. So I by A is pretty much base by hypotenuse, which is nothing but cos of alpha, right? In other words, cos of alpha is I by A, right? Now alpha is nothing but this angle, right? Alpha is nothing but this angle. That is, the alpha is the angle that the incident light is making with the surface normal, right? How do we find that out? How do we find cos alpha? So again, finding cos alpha is very easy. We will use the dot product. So cos alpha is nothing but L dot n divided by magnitude of L multiplied by magnitude of n. That's our I by A, also equal to I by A. So this is the amount of light energy being reflected per unit surface area from a matte object. So this is what we wanted to calculate, the amount of light energy reflected per surface area, per unit surface area, and now we have it in terms of light ray and the surface normal vector. So now that we have this value with us, this expression with us, what is the intensity of the reflected light that's getting reflected from the matte surface? That's pretty easy. That's nothing but the original intensity of the light I multiplied by this expression, which is the light energy reflected per unit surface area, which is I multiplied by n dot product divided by L n. Again, I should not be using cross here because it has got other implications in vector maths. I'll just remove this as well, and what I'll use is something like I dot, right? So let's say we have got n number of point source of lights in our scene, or let's say we have just got n number of light rays coming from different point sources of light in our scene. So how do we calculate the resultant intensity of the light coming from a point on a matte surface? Very simple. We simply take the summation of I equal to 1 to n for n light sources, I suffix I multiplied by n dot li divided by n and li, right? So this is the expression that we need to calculate in our code. So that's matte surface light reflection, and let's see how we can code it. Before that, there is one elephant in the room that we need to address. That is, how do we calculate the surface normal? How do we find out a vector for the surface normal? So let me just make some space. Okay, so finding surface normal is not an easy task. For a given random surface, finding the surface normal is a complicated thing. But in this case, in our case, we are kind of saved because the objects that we are considering are spheres, and for spheres, finding the normal is very, very easy. So let's say this is a sphere, right, with center C, and this is a point on the surface P, and this is the normal N. For a sphere, the normal is nothing but P minus C, that is the normal vector. And finding the unit normal, because most of the time the surface normals we consider will be unit vectors, so finding this is very easy. We just take the mod, we divided it by the magnitude of the same thing, that is P minus C. So in short, the surface normal at a point P on the surface of a sphere is nothing but, if that point is P, then it's nothing but P minus C divided by magnitude of P minus C. So that's it. Let's try to convert this into code and see how it changes or how it impacts our rendering. This is where we left our code last time, and let's try to add lights, some point source of light and some directional lights. And remember, ambient light is nothing but a constant value that we will add to our final resultant intensity of the light being reflected from a point on the surface of the objects. So what we are going to first do is, let's define a type for our light, and we'll define it below our, let's define it below the sphere type. So type def struct. So primarily we will have, okay, we will call it light underscore t, and it will have a type. Right now it will simply be integers: 0 for ambient light, 1 for point source, and 3 for directional light. We will have an intensity, and we will have a vector. For point source it will be a position vector. For directional light it will be the vector for a light ray. It will represent the direction of the directional lights. Okay, so light vector. Okay, next let's add a array of lights. Light T. For the starters we will just have 3 lights, and so first let's add ambient light, and location really doesn't matter, but I'll just give the origin as its location. Then we will add a point source. We will give its intensity as 0.6, 2,1, 0, and finally we will have a directional light, and we will give its direction as something like 144. Okay, and another thing we will need to do is, now our scene, which earlier used to just contain the array of spheres, it will also contain the array of lights. So we'll simply do light underscore t, and we will finally do scene dot lights equal to lights. Okay, now the most of the changes that we will be making is in the trace ray function, right? Earlier we would just return the background color. Sorry, earlier we will just return the color of the surface of the sphere hit, that is the closest sphere that our ray hit. But now we will multiply that color vector with the intensity of the light that's bouncing off that surface. So for that we will need to first calculate the intensity. So let's do that. So we won't be returning this return close thing anymore, so let's get rid of this. And remember, what we have from here is the closest sphere, and when we are tracing the light ray, the two things that we have is the closest sphere where the light ray is hitting, and also the t. So our light rays, basically we are representing our light rays using the parametric form of a vector, which is origin plus parameter t into direction d, so o plus td. And now, so p equal to o plus td, and we can find out any point on the ray by changing the value of t. So now basically we will find out the point on the surface where the ray hit, and doing that will be very easy because we know the direction of our light ray, that is radii r. We know where it originated from, right? It originated at the origin, which is nothing but our camera. And the third thing we needed, the most important thing we needed, was the t, the parameter t, and we already have figured it out from our previous calculations from the quadratic equation that we solved. So now let's find out the point, and for that the first thing we need to find out is t times t, right? So let's do that. I'll create a vec3 which will be t, which will call t times d ir, or direction equal to constant multiply. So again, t is a constant, d is a vector, so we'll do day direction and day dir with, we'll multiply day dir with closest t, right? And then finding out the point is easier because we'll just simply do vec3 point equal to add origin comma t times dir, right? That is the point we got. And now we'll find out the surface normal. which is like, as explained earlier, is pretty easy for spheres, and that will be vector subtraction. That will be pretty much p minus c. I'm not yet making it a unit vector, but I'll do it soon. We'll send the point and the closest sphere's center. Okay, and let's now just convert this normal into a unit vector. So constant multiply the normal that we just got and 1.0 divided by the magnitude of the normal. That's pretty much it. And let's create a function called compute lighting now, which will actually take these values and give us the resultant intensity of the light bouncing off from the point on the surface. Let's create that. So what compute lighting will return at the end of the day is a constant, which is intensity. Hence the return type float should be enough. And vec3 will have point vec3 normal. So these are the things that we'll be requiring. We'll be requiring the point where the light ray is hitting. We'll be requiring the normal, the scene of course, so that we know the spheres and we know the lights. That's pretty much it that this function will be requiring as of now. When we'll be adding specular reflection, that is basically adding shine to objects, at that point of time we will be adding more parameters to this function, but as of now this is fine. Let's start with a float I equal to 0.0, and now we'll pretty much loop over all our lights. So let's pick a light. Okay, and if light dot type equal to 0, then it's pretty much a ambient light, right? So we'll simply add its intensity. Else we will create a vector called light direction, and we will initialize it with 0 0 0. If light dot type is 1, which means it's a point source of light, then light direction will be, so for a point source of light, the light direction will be, remember we will consider a vector coming from the surface to the light, so it will be pretty much subtraction between light dot light vector and point. So we'll consider the vector that's originating at the surface point and going towards our point source of light. So again, for point source of lights, light vector is nothing but the position of the light. So this light vector that we defined in light type, for point vectors or point source of lights, this light vector is nothing but the location of the point source of light in the scene. Maybe I could have named it a bit better, but I'll stick to it as of now. Okay, else what we'll do is light dir equal to simply light dot light vector, because for directional lights, light vector is actually the direction of the light ray. Okay, now what we need to calculate is the dot product. Remember, what we are trying to calculate is this expression. The first thing we need to calculate is the dot product between the surface normal and the light vector. So let's do that. And again, dot product is a scalar quantity, so I'll call it normal dot dir equal to dot normal light dir. Okay, and if normal dot dir norm dot dir is greater than 0, we do I plus equal to, of course, light dot intensity, because remember, the final intensity will be the actual intensity multiplied by this expression. So intensity into or multiplied by norm dir divided by the magnitude of light dir. So we don't have to do the magnitude of normal, because this factor here is already 1 because it's a unit vector, right? We have already done that. And finally what we do is we return this I. Sorry for so many typos. I have recently changed the configuration of my mic and I'm not that good of a touch typer, so I'm just missing some of my keystrokes, but I hope I'll get used to it. Okay, so that's our compute lighting function. What we will now do is we'll call it from traceray and we will multiply our closest sphere color with this intensity. So it will be a scalar multiplication. Okay, so what we will return from here right now is constant multiply and closest sphere dot color comma compute lighting. We will send the point, right, the point where the light ray hits, the normal of course, and the scene. So that's it. And from the main method, what we'll do is, now we are already getting back the color. So one thing that we'll try to make sure here is the value that we get in return from traceray, the color vector. Each value in that color vector should be within the range 0 to 255 so that it's actually visible light or visible color. So this is just a safeguard we will put in place, just a guardrail that we are not dealing with garbage values. Okay, so first we will create a function called clamp color val, which is responsible for clamping the individual channels. So let's do that. So it will be pretty simple. Clamp color val float color val, and if color val is less than 0, then we'll simply return 0. If color val is greater than 255, we'll simply return to 55, or else we'll return color val. Okay, and using this we will create the function called vec3 clamp color, which will take a color vector and we will return a new vector vec3, which is pretty much, we will apply the function clamp color val on each component of the color vector. X dot y z. Yeah, so that's pretty much it. Okay, and now what we will do is we will call this function here and we will draw it on the screen, right? So that's it pretty much. That's how we add light sources to the scene and we deal with matte surface, right? And now let's try to compile it and see how it looks. Okay, we have got a typo. It will be dot, and there seems to be some issue. The color is not getting rendered properly. Let's see, what is it? The black spheres didn't look really good. Let's try to fix it. Okay, I see what happened. I didn't malloc the array. Let's see if now it works. Oops, there's something else, I believe. Okay, so here I believe is the issue that's happening. So it will be float instead of int, so that so since it was int and we were passing 0.x values like that, it was rounding it off to 0, or it was basically floating it down to 0. And I believe now it should be fine. So now let's see how light impacts our meta objects, and I'll do a mcgen. So see, now we have got the feeling of a volume, and it looks much different than our initial image, which was pretty much two-dimensional and flat. Now we are getting a feeling of a volume for these spheres, and now you can actually see how the brightness of the light is different, or the brightness of the color. The brightness of the color is different in different portions of the spheres, right? Which actually is giving the feeling of the curvature of the sphere. So that's how matte surfaces behave, and that's how dispersion reflection happens. So next we will try to add a shine to these objects, which is also called specular reflection. So yep, let's see how we can do that. Okay, so now we will discuss about shiny objects or shiny surfaces. So this is also known as specular reflection. So what are shiny surfaces? So if I put it in a very naive way, shiny surface is any surface that has got a shine, right? So what is a shine? So if we look at a polished plastic ball, or a polished any plastic surface, or a steel surface, or anything like that, which is nicely polished, we will see that along with the color that the surface has got, we will see a tiny white spot on that surface, which moves as we move around that surface. So if you look at a shiny object, it usually has a tiny dot, a tiny white spot on that surface, which moves. So its position depends on how we are observing it, right? It moves with us. So that tiny white spot gives a surface the shiny effect. But why does this occur? Why does this surface has a shininess? So as mentioned in case of matte surfaces, a surface is matte because a matte surface or a non-shiny surface is not that smooth, it's not plain, it's usually rugged, it's rough. If I zoom into a matte surface, or a rugged surface, or a rough surface, what usually we will see is something like this. So from a macroscopic level, what we usually see is something like this, pretty much a plain surface, right? A plain straight line. But if we go a bit deeper, what we would see is the surface is irregular like this. So it has got tiny ups and downs, pretty much like a mountain, right? The surface will be like this. So now, as you can see, if any light ray falling on this surface, like for example, they will always follow the laws of reflection, right? So the angle of incidence will be equal to the angle of reflection. So technically they will reflect the light ray only in one direction, but in this case, in a matte surface, this light ray can fall on any such subsurface, right? It can fall. So if the light ray hits this surface, it gets reflected here. If the same beam of light, which means the rays which are parallel to this ray, if another ray from this beam of light, it falls on, let's say, this surface, okay, it's not that parallel. Okay, if it falls at this surface, then its reflection will be something else, because the normal will change and it will reflect somewhere here, right? It will reflect in a completely different direction compared to the first ray, and same goes for this surface. As a result, this is the reason I made the statement previously that light rays falling on a matte surface will get reflected in all possible directions, right? There is no one specific direction in which it will get reflected. Now let's say this surface was not that much irregular, but it was somewhat irregular. So let's say the surface is somewhat like this, and it's plain. It doesn't have this mountain like or ridges. It doesn't have this mountain like structure. So any ray that falls on this surface, the surface normal will always be pointing at the same direction, and it will always reflect back at the same direction no matter what, because the surface is regular, right? No matter how many rays you considered here, it all will get reflected in the same direction. That is, let's say along this ray, right? Say for example, L will get reflected along R, L dashed will get reflected along R dashed, and if L is parallel to L dashed, this would imply that R will always be parallel to R dashed. Sorry, R dashed, right? So that's the property of a very polished surface, which might act as a pure reflector. That is, all the light rays falling at the surface will get reflected at the same direction. Of course, all surfaces are not that polished. So depending on how polished the surface is, a given random reflected ray will be close or far away from the actual reflected ray. Okay, so what I'm trying to say is, if I consider a polished surface, a very well nicely polished surface, what happens is, if let's say, okay, so this is the normal, and let's say a ray of light falls somewhere here. So ideally, if this surface is nicely polished, it should be reflected, let's say, in this direction. Okay, let's just change the direction once again. As per our convention, the light vector is represented from the point P towards the light source. So let's say this is L, and this is R, and this is our arrow. Okay, now this is the ideal case. This is when the surface is very polished and it goes extremely polished and it goes towards R. But if the surface is not that polished, what might happen is, for this ray L, we might get reflected rays which point to different directions, but which are closer to R, right? That's when the surface is semi-polished. We might get a ray somewhat like this, like which is going this side. We might get another ray which is going like this. Now the more polished the surface will be, the closer the reflected ray will be to the actual reflected ray, or the ideal reflected ray, right? There is no actual reflected ray, but the ideal reflected ray according to the law of reflection, right? So another ray might be somewhat like this. Okay, so this can be another ray, and so on. And let me name these. Let this be R dashed, R double dash, etc. The more polished, or the nicer the polish of the surface is, the closer the reflected ray will be to the ideal reflected ray, and that determines how shiny the object is. Lesser the angle between the reflected ray and the ideal reflected ray, the shinier will be the surface, right? In order to find out the shininess of our surface, or to project a given shininess for our surface, what we would want to do is, let me just quickly get rid of these rays. What we will consider is a ray which is reflected from the actual incident ray L, and which is coming towards our camera or viewing point. So let's consider such a ray. Oh, let's say this is that ray, and we call this ray V. So this is the ray which is coming to our camera, right? And this is supposed to be a reflection of this ray L. And let's consider an angle alpha. Now, as we mentioned earlier, the closer the value of alpha will be to 0, the shinier the object will be. The reason is, if alpha tends to 0 or alpha becomes 0, it means all the light is being reflected towards our camera. In other words, our camera is receiving more of the reflected light rays. More alpha will be going towards 0, the shinier the object will become. The more alpha will increase, the more will be the distance between this reflected ray V and the ideal reflected ray R, the lesser will be the shininess. Rather, shininess is inversely proportional to the angle alpha. So now we need to mathematically define the shininess of an object. How can we convert this qualitative analysis into our code? So what we'll do in this case is, we will try to come up with a mathematical model which fits in with this situation, right? And one such model, or one such mathematical function, is cos. So if we think about cos alpha, so cos alpha tends to 1 when alpha tends to 0. And either way, when alpha increases, here the maximum alpha that we will consider is 90-degree, right? Because after that the reflected ray will go inside the surface, and we don't want to consider that. So the more alpha will increase and it will tend towards plus 90-degree or minus 90-degree, the value of cos alpha will keep on decreasing, and at a point of time it will become 0, right? If I plot alpha with cos alpha in this case, so the graph that we will get will be the classic cosine graph, and it will be something like this. So it's 0 here, and if I draw the y-axis, it's pretty much plus 1.0. This is 0, and whenever alpha is, as alpha will increase, the value of cos alpha will decrease both ways, right? And it will peak at alpha equal to 0. So this perfectly fits our model. Now the only thing is that if we directly apply this model into our code, all the objects will kind of have the same shininess, right? We don't want that. We should be able to give different objects different shininess. So for that, what we can do is we can raise the value of cos alpha to a positive exponent, because if 0 is less than cos alpha less than equal to 1, even if we raise it to a power, let's say s, still the relation will be there. So still 0 will be less than equal to cos alpha less than equal to 1, right? So this s will be our the shininess factor, how much shiny an object will, because the more the value of s will be, the narrower this graph will become at 0. So for example, for a very high value of s, let's say for s equal to 1000 or something, it will become very high like this. Again, if we decrease s a bit, we will get a more relaxed curve across 0. Let's say this is something like s equal to 500, and so on. What this essentially signifies is, for a tiny change in the value of alpha, the value of cos alpha will change rapidly. The more rapidly the value of cos alpha changes with the change in the value of alpha, the shinier the object will be. So it's like for a small movement of the ray angle, the shininess will vary rapidly, right? And the shinier the object will be. That's how we are going to determine the shininess. So for shininess, pretty much we are calculating cos alpha and raising it to the power of s, and alpha is nothing but the angle between the viewing ray, the ray that comes from the point on the surface to our camera, and the ideal reflected ray from L. So let's see how we can calculate the alpha. Once we have alpha, we can easily calculate cos of alpha. But before we can calculate cos of alpha, what we need to find out is the vector for the reflected ray r, right? Somehow we need to find out r from a given incident ray L. So let's try to do that first. This is our surface. Let's say this is our point. This is our incident ray. This is our reflected ray. And this is our normal, right? Okay, so now let's just label them. This is N, this is L, and this is R, right? So we have L. What we don't have is this. We don't have R. So what I'm going to do now is I'm going to split L into two vectors. So I'm going to split L into x component, and I'll name it, let's say this is the x component, and I'll name it something like LP. This is LP, and I'll also split it to a y component. This is the y component, and I'll name it LN. I'll name it LN because it's parallel to N, the normal, surface normal. What I will do is I'll simply translate this LP vector to top. So I'll simply translate this vector to here, right? And by laws of vector translation, this also becomes LP. So this also becomes LP, okay? If you apply the classic formula of finding a resultant vector by completing the triangle, you can see that this ln and lp are two vectors, and l is simply the resultant vector which we get by completing this triangle that is being formed by ln and lp, right? So we can say l is equal to ln plus lp, right? So now what we will try to do is we will try to find out lp. Why we want to find out lp and why we want to do that, that will be clear in a moment. Let's see if we can find out lp. So lp is nothing but lp equal to l minus ln, right? And so what is ln? Ln is nothing but the projection of l on n, on the normal, right? If we just apply the classic projection finding formula, so mod of ln is nothing but mod of l, and let's consider this angle is something like theta, right? So there's an angle that l is making with n, the surface normal, or rather this is the angle of incidence. So it's nothing but mod l into cos of theta, right? And what is cos of theta? Cos of theta is nothing but the dot product of l with n divided by mod of l divided by multiplication of the individual magnitudes, right? That's pretty much your cos theta. So now what happens? L, magnitude of l and magnitude of l cancels out, and what we are left with is mod of ln equal to dot product of l and n divided by the magnitude of n. Now remember, n is nothing but the surface normal, which is a unit vector. So this gives us ln mod is nothing but, I mean, the projection of ln on y-axis is nothing but l dot n, right? So that's the projection, that is the magnitude of ln. And if we want to find out the vector ln, we simply give this l dot n a direction, and we can easily give this direction by multiplying it with n. So it becomes n multiplied with l dot n, right? So that is our ln. So ln is nothing but surface normal n multiplied with the dot product between l and the surface normal, right? So this is the ultimate result that we'll be using. So let's once again clean this part up. So for some people this will be very intuitive, like people who already know about getting the projection of a vector along a particular direction, but I just wanted to show the calculation or vector maths. So now what we know is the results that we have is ln is nothing but vector n multiplied by n dot l, right? And then lp will be something like vector l minus n multiplied by n dot l. So now let me complete this triangle. So we have ln, we have found the value of ln, right? And if we can somehow find this vector, then r will be nothing but the vector summation of this ln and this vector which goes from this point to r. So how do we find it? This is nothing but minus, like, the negation of lp, right? Why this is a negation of lp? Because remember, this is the ideal reflected ray. This angle of reflection is equal to angle of incidence, so this is also theta. No doubt both of these angles are 90 degree, so both of these angles become 90 minus theta. This also becomes 90 minus theta. This is an isosceles triangle. Since we have an angle bisector, these These individual, this LP and minus LP, are nothing but the half of the base of this triangle. So now we just need to find out minus LP, and what then we will do is R will be equal to Ln minus LP. Now we know Ln equal to n vector into n vector dot product L, minus LP will be nothing but minus L, and LP we know it's again minus n into product of n dot L. We are already doing a minus here, so this minus will become plus, and it will become plus n dot L. We will simplify this a bit, so this becomes nothing but 2n into n dot L minus L. So this is what R is. Once we have R, and let's say this is our view vector, or the vector that goes to the camera, and this is the angle alpha, then cos of alpha will be nothing but cos of alpha equal to R dot V divided by their magnitudes, the product of their magnitudes. And we already know what R is, right? So this seems a bit complex. It seems the expression is pretty large, but it's not actually that large. When we will code it, it's actually, we already have this individual values, so we'll just have to use our vector utility functions to calculate these, and it won't be that difficult. Now remember, the final thing that we are after is the intensity of this ray, because that is what we will use to multiply with our final color of the surface. So that is our final goal, getting the intensity. So the final intensity of this ray will be nothing but the original intensity, the intensity of the original incident ray multiplied by this cos alpha. So we will simply multiply, so I dashed, or the I intensity of the reflected ray, will be simply I into cos alpha, and the value of cos alpha we already know. So if I just put it here in an elaborate way, so I is nothing but I dashed is nothing but I into, or multiplied by, R dot V divided by R V. We need to remember that we already have the matter deflection intensity as well, so we will simply have to add that thing here as well, which was nothing but n dot L divided by mod n into mod L multiplied by mod L. So this becomes our total expression of the final I. And to complete, for the sake of completion, we can also add the IA, which is the ambient light. This becomes the complete expression for the intensity of the light bouncing off from a point on the surface, considering the mattiness or the dispersion reflection, the specular reflection, which is this shininess, and the ambient light intensity present in the scene. So now we will incorporate this shininess into our code. Let's do that. Okay, so let's now write the code for shiny objects, or to implement shiny objects. So for that, what we'll do is, first we will make some changes in our compute lighting function. We'll do is, we will make this function accept two more parameters. One is vec3 star point to cam. So this is basically our vector v. Usually the ray direction is what gives us the direction of ray from camera to the point, but this gives just the reverse of that. We'll see how we get this. It's very easy. This is our ray v, and the other thing we want is the shiny factor, or the specular, we call it specular here. So the shiny factor of every object. So now what we do is, like, every object need not be specular, right? So the objects which are not shiny, we will denote that they are not shiny by putting the value -1 for their specular factor. So if specular not equal to -1, okay, so the first thing that we will need is a dot product between our surface normal and the light direction, right? But if you see, we already have that. That is nothing but this norm.dir, right? The other thing that we want to calculate is this factor. So basically we want to calculate 2 times the dot product between surface normal and the light direction and multiply it with the surface normal. So remember, n dot L is a scalar, 2 is a scalar, only vector in this portion of this component is n. N is the surface normal vector. So we'll call it something called, let's give it a name, prefix, because this is pretty much the first component of this one, this 2n n dot L minus L. But anyways, like maybe it's not that great a name, but I'll just stick with this. So constant multiply normal comma 2.0 into 2 times norm dot dir, right? And now we can easily calculate the reflected ray, which is nothing but subtraction between this prefix and the light dir. So the prefix is pretty much this 2n, 2 multiplied by n vector multiplied by the dot product of n dot L, and we subtract L, the light vector, from it, right? And now we have the reflected ray. And now what we want is, we want to find out the dot product between this reflected ray and the ray and our view vector, which is a vector which originates at the point and goes to the camera. So let's do that. Float again, since it's a dot product, it will be a scalar. So let's name it r dot point to cam, and we'll do dot and r comma point to cam, and we'll just multiply it with 1.0. And once again, as normal, we will check if this dot product is greater than 0. Only then we will consider this value. So this is just the dot product. We still have to divide it by the multiplication of the individual magnitudes of the view vector and the reflected vector. So light dot intensity into pow r dot point to cam divided by magnitude of deflected ray multiplied by magnitude of point to cam. Also, this is what we are getting is pretty much the cos of alpha, right? The cos of the angle between the view vector and the reflected ray. So that is r, the dot product between reflected ray and the view vector divided by their individual magnitudes. And we also need to raise it to the power of specular, and we'll just multiply that as well with 1.0. Very similar to our matte reflection or our dispersion reflection. Once again, we multiply the value of cos alpha, which is r dot point to cam, divided by the individual multiplication of the magnitudes of the reflected ray and the point to cam or the view vector, and we raise it to the power of specular using the pow function, right? And we multiply the value of cos alpha with the original intensity of the incident light ray. And finally, yep, so that is it. And now we need to make some change in the calling function. So it's showing error because we need to send this function, these two things as well, specular and this. We'll do that. So let's first define point to cam, which is constant multiply ray dir and minus 1.0. Why so? Because ray dir is nothing but the direction of the ray going from the camera to the point, and view vector is nothing but the reverse of that. So it's the direction of the ray coming from the point towards the camera. So now that we have that, what we'll do is simply pass this. Not to forget, we also need to pass, we'll have to pass a reference and not the variable itself. And also we need to pass another thing, which is the specular factor. And for that, what we'll do is we'll give our sphere structure or sphere type a new property called specular. We will give some specular values. So for the first two sphere, we will give it 500. For the next one, we will give it 500. Let's give this one 10, and let's give this one 1000. And we will pass this specular factor here. Tar specular. Yep, that's it. Hopefully we haven't made any errors. So let's try to run this once. Okay, now we have got this nice shiny effect. So for the red sphere, which is 500, we have got this tiny effect. Blue one is not visible. Again, the shininess depends on how we are viewing this sphere, right? So for this angle, the shininess is not visible. For green, we have a very spread out shininess because the specular factor is 10, and the yellow one is, of course, although the value is high, but it's hidden behind these three spheres. Yep, so that is how we can give a shine factor or a shininess to our surfaces in our scene. Now our scene looks much better, or rather our spheres look much better than what it was in our previous video, which was just flat surfaces. Now we have got a sense of volume, a sense of curvature, and also we know how to use different kind of surfaces or how to implement matte surfaces, shiny surfaces, and how to implement lights in the scene and different types of lights. So in the next video, we will try to see how we can add shadows and reflection. And yep, that's it for this video. Hope you all like this video, and see you all next time.